We have an example problem here. A 0.640 meter long gas column is open at both ends. Question A, what is the fundamental resonant frequency of the air column if the air temperature is 24 degrees Celsius? Question B, what would the fundamental resonant frequency be if the column was closed at one end? All right, so L, 0.64 meters. In this first part, we're given the temperature, which will allow us to calculate for the speed of sound. So our equation that we have for the speed of sound, 331 meters per second times the temperature in degrees Celsius plus 273 all over 273. So plugging this temperature in, that will give us the speed of sound. So 24. .345. And again, I'm going to keep a couple digits past that because this is not a final answer. So we're told at first that this gas column is open at both ends. So this is an open pipe. Our equation for the frequency in an open pipe is mv over 2L. Fundamental means m equals 1. Resonant frequency, the fundamental resonant frequency means our fundamental frequency. Standing waves are an example of resonance, and so that's why what that term resonant frequency means. So F1 will just be V over 2L. We have found the speed of sound at this temperature, and we have the length, so divided by 2L. So we actually only have 2 sig figs here. 270 hertz will be the resonant frequency, this fundamental frequency in this pipe. Question B, we want to know the fundamental frequency if the column was closed at one end. So an open closed pipe, F1 would be V over 2L. Oh, just kidding, sorry, that was V over 2L was what we just did. Open closed, we have that factor of 4L. And so this is essentially half of V over 2L, which is what we just found. So half of our 269.72. So this will be about 130 hertz. Because this comes out to be 134.86 and so forth. So rounding this to 2 sig figs is where I'm getting the 130. And so the resonant frequency in an open closed pipe is half what it will be in an open pipe.